Financial markets generate data characterized by noise, non-stationarity, and chaos. During periods of stress, the standard relationships between asset prices fracture entirely. Traditional econometric models, like ARIMA and GARCH, require rigid assumptions to function. When correlations break down and nonlinear market dynamics take over, these models suffer catastrophic performance degradation. Quantitative analysts solved this by transitioning to deep learning systems. These networks automatically extract complex features and patterns from raw data, bypassing human-engineered rules. This transition generated a prevailing misconception within the industry: the assumption that because transformer architectures are the newest and most complex, they have universally rendered legacy models, like LSTMs, obsolete in quantitative trading. In quantitative finance, architectural superiority is never absolute. An algorithm's predictive power is strictly conditional on the structural realities of the data it processes. This flowchart maps the evolutionary branches of neural networks deployed in modern asset pricing. The upper branch tracks recurrent neural networks, evolving into long short-term memory networks, or LSTMs, and GRUs, specifically designed to solve the vanishing gradient problem in sequential data. The lower branch shows convolutional neural networks, which laid the groundwork for processing local features, eventually leading to the transformer and its ability to model global dependencies. To understand why elite trading desks still rely on both branches, we have to define the exact mathematical boundaries where each of these final nodes actually wins. Successful quantitative strategy design requires matching algorithmic properties to data frequency and constraints, not just deploying the newest technology. The core challenge of sequence modeling is teaching a system to retain relevant market states over time, while actively ignoring temporary noise. This diagram shows the mechanical solution provided by LSTMs: selective memory gating. The forget gate physically filters out irrelevant daily price fluctuations, preventing bad data from corrupting baseline memory. Simultaneously, input and output gates actively update the state, maintaining context across 50 to 500 time steps. This gating mechanism perfectly aligns with volatility clustering, a financial phenomenon where current periods of high volatility reliably predict future high volatility. Because LSTMs dictate what to remember and forget step by step, they natively adapt to these time-varying regime shifts without requiring engineers to manually recalibrate the model. By isolating signal from noise over time, LSTMs are structurally optimized for capturing medium-term trends and acting as filters for macroeconomic relationships. However, shifting the environment to ultra-high-frequency TIC-ADA, non-local temporal dependencies dominate. In this environment, the LSTM's strict step-by-step sequential processing begins to lag. This matrix grid illustrates the transformer's core innovation, the self-attention matrix. It computes the pairwise relationships between all positions in a sequence simultaneously. Instead of waiting to evaluate a 1,000-step sequence one point at a time, the transformer evaluates the entire timeline in parallel. This attention mechanism naturally bypasses uniform weighting. To predict an earnings reaction, it dynamically assigns higher weight to past earnings announcements, while ignoring the irrelevant days in between. Using multiple attention heads, the model can track long-term momentum on one pathway, while simultaneously monitoring short-term mean reversion on another. For the transformer to justify its computational cost, two exact conditions must be met. The data sequences must exceed 500 time steps, and the environment must be high frequency. Transformers mathematically win when establishing rapid, global context across vast datasets is more valuable than maintaining strict sequential order. The utility of attention extends beyond temporal history. It can also evaluate cross-sectional relationships between peer assets. This graph represents financial markets as complex network structures, where sectors, supply chains, and assets continuously influence each other. Cross-sectional attention learns exactly which peer stocks provide the most relevant predictive information for a target stock, dynamically adjusting relationships as market correlations shift. Traditional models, locked into fixed mathematical transforms, miss these transient correlation structures entirely. The ability to dynamically weigh shifting multi-asset correlations is the decisive factor that makes transformers dominate in high-dimensional factor investing. If self-attention captures global dependencies so effectively, why are LSTMs still widely deployed for weekly and monthly rebalancing strategies? This boundary matrix maps exactly where each architecture mathematically fails, based on sequence length and data frequency. The transformer's operating zone sits squarely in the high-frequency, long-sequence quadrant. Conversely, LSTMs dominate the low-frequency, short-sequence quadrant. The ultimate constraint that governs these boundaries is sample efficiency. These charts compare data volume requirements. LSTMs require 40 to 60% less training data to achieve mathematical convergence compared to transformers. If you apply a data-hungry transformer to low-resource macroeconomic data, it lacks the volume required to train its massive parameter count, resulting in catastrophic overfitting. LSTMs excel in these low-resource environments, extracting reliable signals from sparse data points without memorizing the noise. Deploying a transformer for a 50-step monthly prediction is mathematically irresponsible and computationally wasteful. Data scarcity and sequence length create a hard boundary. The transformer is a highly specialized tool for high-dimensional data, not a universal replacement. To understand the true value of either model, we have to observe how they operate within a complete production-grade system. This diagram illustrates an end-to-end machine learning trading pipeline. The sequence model is just the central inference engine. It relies on the upstream feature engineering module for clean data, and its outputs are governed by the downstream risk control module. An architecture's predictive power is entirely bottlenecked by the quality of its input features and the mathematical rigor of its risk allocation. Ultimately, performance comes down to the human architects designing these pipelines. The myth of absolute algorithmic supremacy fails under the weight of empirical evidence. Elite quantitative teams do not chase the newest algorithm. They seek maximum information extraction at the lowest possible computational cost. Engineering market memory requires bounding theoretical hype with rigorous empirical constraints. In modern finance, there is no single best model. The optimal architecture is dictated entirely by the precise granularity, frequency, and sample size of your target data.